Okay, we don't have a ton of time for this, but look what I wrote on the board. I think I wrote a couple something. It's just kind of cool, I think. Actually, I think it's very cool. So we talked about the other day our rotation matrices. And so the rotation matrix for 45 degrees looks like this. And the rotation matrix for 30 degrees looks like this. Okay, right? We gotta memorize that's what our rotation matrices look like. So I went ahead and actually filled in the numbers here. So the cosine of 45, I know is root 2 over 2, and so on. So I filled in, created them, and I multiplied them together. So here's the 45, here's the 30. You with me? So I multiplied them using row times column. So for example, root 6 over 4 plus negative root 2 over 4. That's where that number came from. And then I did this row times this column, same thing, and that's where that number came from, and so on. So this is the matrix I get when I multiply the 45-degree rotation times the 30-degree rotation. But then when I look at those numbers, I think I've seen those before. Do you remember those? Seeing things like root 6 minus root 2 over 4? Oh yes, you've seen those before. Where have I seen those before? When I did the cosine of 75, for example, and that's cosine 45, cosine 30, sine 45, sine 30, and when I plug the numbers in, remember that? We did a whole bunch of those, folks, so yeah, that happened. And here's the sine of 75. Same way, this is the formula off your reference sheet, plugging in the numbers, and that's what I got. Wait a minute. The cosine of 75, using my formulas, is that. Isn't that exactly what's right here? I mean, I didn't combine it there, but isn't that exactly the same thing? And the sine of 75 is this, and isn't that exactly what's right here? So this is the cosine of 75, and the sine of 75, and the opposite of the sine of 75, and then the cosine goes backwards, but it's the same thing. Whoa, wait a minute. So how did I get this matrix right here? This matrix is the 75-degree rotation. How did I get it? By multiplying the 30 and the 45. I want you to think about it for a second. If you take something and rotate it 30 degrees, and then you rotate it 45 degrees, isn't the end result going to be that you rotated it 75? So instead of using these formulas, let's say you don't have a reference sheet and you haven't memorized them, you could, let's say you wanted to do 165 degrees. You could do 165 degrees by doing a 120 and a 45, and you wouldn't need any formulas. You would just do the matrix multiplication and it would give you the answers. I think that's so slick, and I'm looking at your faces. I'm sorry you don't agree with me. All right, let's look at our notes now. We need to get back to our notes. We need to talk about some vocabulary. But I think, before I talk about the vocabulary, I think I'm just going to look at the first problem. All right? So I think the vocabulary is going to make more sense to you after we've looked at a problem. So number one, we're skipping vocabulary for a second. We're going to get to it. It says use Gaussian elimination to solve. All right, so the first thing we're going to do, Gaussian elimination is a matrix operation. Okay? It's a matrix operation that transforms the matrix. We're going to do that right now. So we're going to take 1, minus 2, 1, and 7. 3, negative 5, 1, and 14. I'm building a matrix. I am not going to do this on my calculator. I'm going to do it by hand. You will need to do a problem like this by hand eventually. So follow along. It's real easy. Takes a while, but it's really easy. All right, everybody understand where this came from? Look at your problem. Look at this is problem number 1. Look at the equations. Now, do you see where they came from?
Yeah.
Wouldn't 7, 14, and be like the inverse thing where you'd say equals and then the...
They would be the equals ones, but this time I'm putting it all in one matrix. This is called an augmented matrix. It's a lengthened matrix. This column represents the x's. This column is the y's. This column is the z's. And this is the equals numbers over here. A lot of people put a dashed line down there. You don't have to, but that dashed line sort of separates the constants from the coefficients. Kind of stands for the equal sign. All right, now what I'm going to do, notice it says Gaussian elimination. I'm going to do a method of elimination. And my first goal is to make this number right here become a 0. Okay, I'm going to make that a 0. This is your first time, you have no idea what I'm doing. It's okay, follow along. So I'm going to recopy that top row. All right. Now, I'm going to use like normal elimination, only instead of doing it with equations, I am doing it with rows of the matrix. So I am going to take that top row of the matrix and I'm going to multiply that row by -3. Now, there shouldn't be any confusion about why I'm allowed to do that. What does that top row represent? An equation. Are you allowed to multiply an equation by something?
Yeah.
Yes. If you can do it to an equation, you can do it to the row, because the row is an equation. All right, so that's going to give me, some people do it in their head, I can't. So it's going to give me -3, 6, -3, and -21. That's what I get. Now I'm going to add it here because my goal was to turn that number into a 0. So I times this by -3 so that when I add these together, I get 0. So then what am I going to get here? 1, -2, and -7. Now, does that feel like elimination to you? Don't you multiply and then add to cancel something out? I just did it without variables. Okay. Now, I'm going to do the same exact thing. I'm going to make this 0. So now I won't be timesing by -3. Now I will have to times by -2. And that'll give me, I'm going to write them down here, that'll give me -2, +4, -2, and -14. So I took the top row of the matrix times -2. Now, if you can carry that in your head, that's great. I have to write it down. You don't have to write it down. Now you're going to add it. So I get a 0, a 2, a -3, and a -11. Are you still with me?
Does this only work for when it's 1, or do you just have to do multiply both?
You'll have to multiply both rows. Great question. Yeah, it's more fun. It's easiest when there's a 1 there. But if that had been some other number, then yes, you would multiply both rows, just like you do in regular elimination. Great question. All right. One more step, and we're almost done. I'm gonna get one more zero. And the zero I'm gonna get now is right here. I want that number to be a zero. Okay, so I'm gonna recopy. I'm gonna keep track of where I'm going here. I'm gonna recopy my first two rows. There they are, my first two rows. And the reason I'm recopying them is because I'm not going to change them. I'm not going to put any more zeros in them. This one I need to get a zero here. So I'm going to look at my second row now. My second row. And I'm going to say, okay, if I want to add these and cancel that out, I guess I'll have to multiply my second row by -2. And then it will become, this row by -2, 0, -2, 4, and 14. Now I'm going to add it to get that 0. So that's going to give me 0, 0, 1, 3.
How did you know that the 2 needed to become a 0?
We're going to talk about that in a minute. I'm always looking to get these zeros and that 0. I'm always looking for this lower triangular thing here. But here's why. What was our objective? To solve this system, right? Remember that this represents x, y, z equals. So tell me about the bottom row. Z equals 3, right? Z equals 3. Okay, back up a row. This says 1z equals 3. No x's, no y's, 1z equals 3. Kylie, you see why it's nice to have two zeros there?
Yeah.
Now, if I back up a row, this row says y minus 2z equals -7. But I already know that z is 3. So y minus 6 equals -7. So it looks like y is -1. And then all the way up to the top, x minus 2y plus z equals 7. But I know that y is -1 and z is 3. So it looks like x must equal 2. So the answer to the question is 2, -1, 3. Tess?
I'm confused where you got the -2, 4, -2, 14,
You multiply the middle row by -2. Because I want to eliminate right here.
I'm talking about up there in the red.
Multiply the top row by -2.
So multiply 1, -2, 1, and 7 by
Uh-huh.
-2.
Yeah.
So you're always multiplying the top row.
You're always multiplying the top row if you want to eliminate in the first column, yes. But as soon as I went to the second column, I used the second row. I multiplied the second row. All right, so gotta get back to my vocabulary. What I just did, that process is called Gaussian elimination. Gaussian elimination is the process that puts a matrix into what is called row echelon form. Okay, so Gaussian elimination is the process of putting a matrix in the row echelon form. Now, we're gonna do another one, so don't panic, just stop and listen to this vocabulary. What are the processes? What are the things that I did to make this happen? Well, I multiplied rows, right? I added them together. And back to Sabrina's point, I didn't have to do this, but I like to have that number be a 1, if at all possible. So sometimes I have to rearrange my equations. Is that legal? Sure, it doesn't matter which equation is on top. So you are allowed to interchange rows. You're allowed to move the rows around to suit your purposes. Now you gotta do the whole row. You're allowed to add them together. And you're allowed to multiply by whatever you want. Those are called the elementary row operations, but those are the things we do when we do Gaussian elimination. Now, what does it mean for a matrix to be in row echelon form? It means it looks like this. So there are two components to that. First of all, the first non-zero number in every row, the first non-zero number in every row needs to be a 1. So the first non-zero number in each row is 1. And then every entry or every number beneath those ones has to be a what? A 0. So every entry beneath the ones is a 0. Once you have your matrix looking like that, then this system is easy to solve because the bottom row, Catherine, are you okay? You need to go to the nurse? Honey, go do what you need to do. Whatever the bottom row is, it's going to tell you Z, or whatever your last variable is, and then you can just use your back substitution to work your way up through. One more comment, and we're going to try another one. We're going to skip the calculator program and go to number 3. One more quick comment. Back to Tessa's question. I hope you all understand, I got a lot written in here on this, why I didn't, to get this 0 right here, why I didn't just use my top row. What bad thing will happen if I add the top row and the bottom row? That 0 disappears, and I need it. So, general rule of thumb, back to Tessa's question, I already told her this, but kind of quickly. If you are, these are the first zeros you're going to get right here. You're going to get the zeros in column 1. When you are getting zeros in column 1, use row 1. As soon as you move over here, it's going to be the next 0 you get. As soon as you move into column 2, then you're going to be using row 2. And if we had a bigger matrix, which I'm not going to make you do this like with a huge matrix, but if we did, the zeros in column 3 would come from using row 3, and so on, however big it is. All right, I know we skipped something, it's okay. Let's look at one more. Let's try number 3 now. And then we'll get our calculator out if we have time and talk about the other thing. All right, so here we go. Number 3. So first of all, I'm going to set my matrix up. And Sabrina, I like the order they're in, so I'm just going to go with that. Because I like that number to be a 0. It makes things easy. Does that look okay to everybody? All right, what am I going to do first? I'm going to turn these two numbers into zeros. And I am going to do that by multiplying the top row by whatever I need to multiply it by to make these disappear. Okay? So, I'm going to go to this one first. What do I need to multiply my top row by? So, -2 to -4, 6. And then add. Neely, did I make a mistake?
No, I made.
So 0, 3, 5, 6. Does that look okay? -5. Thank you. Oh, that can be deadly. Be careful. Is that all right now? How about now the bottom row? Actually, I'm not gonna have to do anything except add. So 0, 1, -1, 4. If I add top and bottom, did I add right? Okay. Now, you do not have to do this, but I am going to put my blue row second and my green row on the bottom. For two reasons. One, it just feels better to me. And second, ultimately, don't I want that number to be a 1? In the end, that number has to be a 1. If I'm doing Gaussian elimination, I have to be in row echelon form. So that number has to be 1. You are allowed at any time to interchange rows, because rows represent equations. You do not have to do that. It's an extra step of writing, I get it, but it's going to make our life easier. We're not going to have fractions, which is what was going to happen up there. All right? So here I go. I have one more 0 to get, and it is right here. Would everybody agree with that? So I am going to go ahead and recopy my first 2 rows. And now what am I going to do to row 2 so that when I add, I get 0? -3. So 0, -3, 3. What did I multiply by? -3, -12. Are we okay? Now, what do I get on my bottom row then? I get 0, 0, -2, -6. Now, you're not gonna like this, but the rules are the rules. Is that matrix in row echelon form? No, because the first non-zero entry has to be a 1. So to be absolutely correct, we need one more step. What are we gonna do to get that to be a 1? Divide, yep. Now we're done. The directions said Gaussian elimination. Now I'm done. Okay? Now let's get an answer. What does that bottom row tell me? Z equals 3. Z does not always equal 3, but apparently it does today. Then what? Y minus Z equals 4.
Yes.
So Y minus 3 equals 4, so it looks like Y equals 7. X minus Y plus 2Z equals -3. So X minus 7 plus 6 equals -3. So what does X equal?
-2.
-2. So your answer is -2, 7, 3. Lucy?
So you can just divide a single row by a number, you don't, like, you can't, it's not
Can you
divided.
multiply a row by a number?
Yeah,
What's division?
yeah.
Yep.
How did we get the, third, like, once you have the second row to 0, 3, -5, 6, what did you multiply by to get it to
I didn't, I switched those rows.
Yeah, we need like the regular elimination so you're able to faster and difficult. That's what we're doing.
We're just doing elimination.
Yeah, but that's like the longer way.
Oh,
But it's like the
no.
longer way. On the last
Okay.
one, last one it definitely.
Now,
the
you,
last one definitely.
okay, I'm not even going there, because you're thinking in terms of a system and equations, it's got 3 equations, 3 unknowns. What if it had 8 equations, 8 unknowns? It gets very unwieldy. Anyway, I'm not gonna argue with you. What I want you to do now is get your calculator out, and we are gonna use Gauss-Jordan reduction on the calculator. So, I want to go back to the first problem. Actually, yeah, let's go back to the first problem. Guys, we're almost out of time. You're not going to know what's going on if you don't be quiet. So be quiet and focus. Okay? Now, that's the original. That's problem 1. I'm doing problem 2 now. So problem 1, I go back to my original matrix here, right? Now I'm going to put it in my calculator. So second matrix, we've already done this, right? Puts things on our calculator. So second matrix, over to edit. What are the dimensions of this? 3 by 4. So in goes 3 by 4, and then here come the numbers. Then anybody remember what we do after we get that last number in? Second quit. Yep, we're done editing. We're done edit. Edit mode is used for one thing, and that is to put the numbers in. Once they're in, you want out of there. Okay? Now, here's what I want you to do. Everybody listening? All right, so I want you to go back into matrix. Second matrix. I want you to go over to math. Now we're going to do something. So you see determinant, trace, you see all kinds of stuff. I want you to arrow down, keep arrowing all the way down until you find R, R, E, F. R, R, E, F. So press enter, and then second matrix, enter again, twice. And a new matrix is going to pop up, and the matrix that pops up looks like this. Okay, now I want you to look at your notes right above, and when we did this problem by hand, what was X, what was Y, what was Z? Aren't they right here? Because as we already had these zeros, but the calculator put these zeros in for us. So what does the top row say? X equals 2. Y equals -1. So there's no need to do any substitution. It just pops right out. What does that RREF stand for? RREF is what we call reduced row echelon form. RREF. And reduced row echelon form says the same thing echelon form does. First number in every row that isn't a 0 is a 1. Look at your matrix, look at your calculator right now, isn't that true? Everything under those 1s is a 0. But what else? Everything above the 1s is a 0.
So it's the same equation, but
Now, if we are using our calculators, I see 0 reason to ever use REF. REF, which is, I don't know if you noticed, but it was right above the RREF. If you REF, it puts the matrix into row echelon form, which means you're going to still have to go back and substitute to get the answers.
I think I just wrong.
So if we're doing a calculator, we definitely want to RREF. Gauss-Jordan reduction is the process of putting a matrix into reduced row echelon form. Gaussian elimination goes to echelon form, regular row echelon form. Gauss-Jordan reduction goes to reduced row echelon form. They are both processes, the end result is a little bit different. A triangular matrix is a square matrix where everything is 0 except the main diagonal that's all ones. So, when I erased mine, but this would be an example of a triangular matrix. The identity, right? The identity is the triangular matrix. So that's that definition. Okay, so next time, okay, we got all our vocabulary covered. So next time, we'll do one more Gaussian elimination, a couple more Gauss-Jordan reductions, and we'll be ready to move on. Okay? All right, good deal.